All right, so yesterday we did our lab on position versus time graphs. Okay, we got those built. We saw that for an object traveling at a constant velocity, there was a linear relationship. That is, the points went up pretty much in a perfectly diagonal line across the graph. So what we're going to look at today are what are some of the things that we can read off of a position versus time graph, and if we get to it, a velocity versus time graph. Okay, what kind of things can we calculate from a position versus time graph, okay, and kind of how those are similar to the formula that we've been using, that is V equals D over T. Okay, questions so far? All right, now you also do guys have a formula sheet. It's on the back of your periodic table. Hopefully you still have that because you're going to need the formula sheet that was on the back of your periodic table for the remainder of the unit, okay, starting next week. All right, so if we have a position versus time graph, a position versus time graph tells us where the object is as a function of time or at various points in time. Okay, so if I'm looking at this first graph with the green line on it, okay, where does the object begin? Ethan? Yeah, it starts at a position of 20 meters. Okay, I would assume that's positive. They don't outright say it. They probably should. It should say north or positive or forward or something like that. Okay, but its initial position is 20 meters. Okay, that's where it is at time zero. What's it doing during the first second here? Nothing. Yeah, right? At time zero, it was at a position of 20 meters. At time 1 second, it's still there. So it didn't go anywhere. Okay. Anytime we see a horizontal line on any kind of graph, that graph is saying that nothing is changing. Doesn't mean nothing is happening. It just means nothing is changing. All right. On a position versus time graph, it means the object's not moving. Right. If this was a velocity versus time graph, then it would say the object's velocity is constant. Right. It would be traveling at that velocity for as long as the line is flat. Okay. Okay, so what's going on then for this object between 1 and 3 seconds? It's going somewhere. Okay, that's a good start. It's going somewhere. Right, it's moving at a constant velocity in a positive direction. Right, it started at a position of 20 meters, and at time 3 seconds, it's at a position of 60 meters. So it went forwards. Right? And it did that at a constant rate. How do I know it did that at a constant rate? Does this graph look like the graph we built yesterday? Or at least this part of it? Right? Each second, it went the same distance. Right? In this second, it went 20 meters, and in this second, it went 20 meters. Right? So it is traveling at a constant speed. That's one of the things we have to recognize from a position versus time graph, because that could be an easy multiple choice type of question on a unit exam. Here's a graph of, here's a position versus time graph. What's happening in this graph? Okay, or tell me what's happening in part A, in part B, in part C, okay, and you'd have to explain that. All right, so in this part here, we're traveling at a constant velocity, and that constant velocity can be calculated, right? If I know my initial position, okay, so if I want to calculate velocity off of a position versus time graph, I take the final position, and I subtract the initial position, and I divide by time. Because what does this calculate? Okay, change in position, which is displacement, right? When we were talking about that the other day with the trip to Walmart, okay, we said that when I got to Walmart, I had changed my position by this much. I had traveled a 4-kilometer distance, but my change in position was only 2.7 kilometers at whatever the direction was. Okay, in this case, okay, we take final position, subtract initial position, and divide by time. So my initial position for this part of the graph is, my final position is 60 meters. My initial position is 20 meters, and that takes 2 seconds. All right, so I got 40 over 2. Okay, so we got 20 meters per second. And that would have to be positive because it's a vector quantity. All right, everyone kind of follow what I did there? Okay. All right, what's going on in this part of the graph? Nothing. Yeah, the object's position is not changing in this part of the graph. Okay, what's going on in this part of the graph? Which way is the object traveling now? It's coming back. Yeah, its position is going from 60 back to 20. Right? So it's coming back. It's retracing its steps, and it's doing it, again, at a constant velocity. All right? Can I calculate that constant velocity? Yeah, same way I did here. All right, I'm going to go final position, 20 meters, minus the initial position, 60 meters, except this time it only takes 1.5 seconds, right? It starts here at 4.5 and goes to 6. Okay, and I've got a negative number on the top because 20 minus 60 is negative 40, right? Indicating that, yes, I am going backwards. So negative 40 over 1.5. All right, so we're looking at, now it's actually moving faster in a backwards direction, negative 26.7 meters per second. All right, so are we doing anything like different than what we did when we had word problems? We're not, okay? A graph is a visual representation of a word problem, right? And that's what we have to be able to recognize, is that when I'm answering a word problem where I'm manipulating v equals d over t, I could, if I had the right information, turn that into a graph and use it. Okay, what's going on in this position time graph? Because in this one, the line's curved. Yeah, what do we call that if it's slowly gaining speed? Yeah, it's accelerating, right? You speed up, okay? Actually, in physics, we use the word accelerate to define any change in velocity. So even slowing down is an acceleration. It's just a negative one, okay? We don't use the term decelerate in physics, okay? An acceleration is any change in velocity, and this is showing an acceleration. Here's how we know that, right? In the first second, okay, so right here, the object only went this far. But in the next second, it went further. In the second after that, it went even further. And again, okay? See how the height of these triangles is getting bigger and bigger, right? The only way for me to go further in the same amount of time is to go faster. Okay, so that's what this is showing us. Okay, the horizontal dotted lines I drew are all the same length because they're all 1 second long. Okay, but each second I went farther than I did the second before, meaning I was also going faster than I was the second before. Right, so if we see a curve on a position versus time graph, okay, that's indicating that the object's velocity is changing. In this case, the object is speeding up. Okay, what if the graph looked like this? Slowing down, yeah. Okay, it's slowing down because here the line is steepest, and here it's almost flat. And we said over here that when the line is flat, the object's not moving at all. Okay, everyone kind of follow how we interpret a graph? Interpreting a graph is a really important skill. Okay, being able to look at a graph and know what it's telling me just from a glance. Okay, move on here. Okay, slope calculations. Now, you guys were already familiar with this, okay? Y equals m times x plus b, so we don't have to worry about this part here, okay? If I want to calculate slope, slope is what part of that formula? M, okay. So if I want to calculate slope using this formula, I first need to move b, so that'll be y minus b, and then I've got to do what with x? Divide by it, right? So this will calculate slope, which is important because it's one of the things you're asked to do in your lab report. Okay, that will get me the slope of the line. Now, what does the slope of this line on a position versus time graph represent? It represents velocity. Here's why. on the last, oh, I erased it. On the last slide here, okay, I had written this formula that V equals final position minus initial position divided by time. Okay, does that setup look a lot like this one? Right, it's something minus something over something else. Well, in actual fact, it's these same variables, right? All my Y values are positions. Okay, all my X values are times. Okay, so when I go Y minus B, let's say I'm using this point right here. Well, that would be my final position. B would be my initial position. It would be my position at time 0, right? That would, you can't get more initial than that. Okay, so I would have final position minus initial position, and X is time, right? So the slope of this line is calculating velocity for me. That's where the formula V equals d over t comes from. It was derived from the slope of a position versus time graph. And you're going to find that actually happens quite a bit in physics. Okay, a lot of the formulas that we'll end up using are actually just the manipulated slope formula from a certain type of graph. Okay, everybody all right with that? So that's one of the things we got to kind of understand and be able to do is identify what does the slope of this graph represent? What does the slope of this graph represent? Because the slope of every graph represents something different. Okay? In this case, for a position versus time graph, okay, we can figure out that it solves for velocity. Okay, what's going on in part A of this position versus time graph? Is it accelerating? It's not curved. Moving. Okay, so it's changing position, right? It's changing position. Is it doing it at a constant velocity? Yes, okay, because it's diagonal. If it's diagonal, we know it's constant. Okay, what's going on in part B? Nothing, right? It's sitting still. Position's not changing, right? What's going on in part C? Turned around and going. What's that? It's going backwards, exactly, okay? Because its position is going from +6 to -10, all right? So it would be like, essentially what this graph is showing is if I did this. So I walk forward 6 meters, and then I stop for a little while, okay? That would be part B. And now I back up at a constant velocity, 16 meters. I can't, I'll run out of room, I'll walk through the wall, okay? And now I'm at part D. What's going on in part D? Nothing. Okay, what's going on in part E? Well, yeah, I'm running. How do you know I'm going faster in part E than I did in the other ones? It's steeper, right? And we just said slope represents velocity. So the steeper the line, the faster I'm going. Okay, so obviously E is the steepest part of this entire graph. So that's where it's going the fastest. Okay, F would be considerably slower. Okay, I want you to see if you can calculate a couple of things for me from this graph. What is the total displacement of this object? 0, right? Okay, that's an easy one. Okay, it's an easy one because our initial position is 0 and our final position is 0. So, okay, we're done. We did this whole trip, but we ended up back where we started. It was like the Walmart trip. Okay, what's the total distance traveled? That's a little tougher. That's going to take you a little longer. You're actually probably going to have to write some things down to get the total distance traveled, because distance doesn't care whether I go forward or backward. 32? Okay. So, how did you figure that out? A was 6 meters, C was 16, 10 back up. Okay, so here's what he did, all right, in case you missed it. In part A, I went from 0 to 6 meters. So in part A, I went 6 meters. In part B, I didn't go anywhere. In part C, I went from +6 to -10. Okay, my displacement there is -16, but for distance, it doesn't matter that it's negative. Okay, in part D, don't go anywhere. And then I go from -10 back to 0. So E and F add up to 10. Okay, everybody follow me there? I just figured out kind of what each section of the graph was worth, and now I add them together. 6 plus 16 is 22, plus 10 more, 32 meters. All right. Okay, assuming the whole trip takes 18 seconds, what's the average speed of the object? Nope. No, it'd be less than that. Okay, average speed is total distance divided by total time. We said assuming the whole trip takes 18 seconds, right? 32 over 18 is going to be like 1.8. Okay, so 1.78, we'll say. All right, these are exactly the kinds of questions that I would ask you on a quiz or a test. Here's a graph, do the following things with this graph. All right. What's the velocity of the object during part C? Yeah. Okay. So we start here, we end here. That takes oh, sorry, no, it's more than that. Okay, so we got 4 seconds here, right? This goes from 6 to 10 seconds. Yeah. Okay, so -4, right? So our total displacement, so remember, V equals, okay, D over T, that's displacement over time. We already calculated our displacement as -16 meters divided by 4 seconds. Okay, so we're looking at -4 meters per second during part C, right? Same calculations you were asked to do with the word problems. Now you're just asked to get that information from a graph instead of from a paragraph. Okay. All right, everyone following how that works? Okay, this graph's a little bit less sane. Yeah. What is the object doing in part A? It's accelerating. Okay, and it's accelerating positively. It's going faster, right? And I know that because the line is getting steeper. Okay, and it gets steeper until it gets to here. Okay, until it gets to right here, then the line stops getting steeper. All right, but it's getting steeper and steeper and steeper until it gets to that point. All right, so at this point, I've got to explain a couple of things to you. And I'm going to explain to you the only thing that I understood in university calculus. Okay? Because I only understood one thing, it was the first day. Okay? He told us that a curve to a mathematician is an infinitely large number of infinitely small straight lines that are all strung together. So essentially what he's saying is when a mathematician sees a curve, they look at it like you or I would look at a low resolution picture. What can we see in a low resolution picture? The pixels. You can see the little squares because that's how a computer makes things. Okay, it just has squares that are on or off. Okay, and so with a curve, you've got these little straight lines. Okay, each one of those little straight lines has a slope. Agreed? And those slopes are getting steeper and steeper and steeper on this curve. Okay, on other curves, those could get less and less steep. They could get flatter and flatter, okay, depending on the curve. So it's possible that a question could ask you this: what's the instantaneous velocity at this point? Okay, so if it asks you to calculate the instantaneous velocity at that point, okay, you can't go, oh, well, I'll just say that it traveled 10 meters in 12 seconds. Because that doesn't calculate the velocity here, that calculates the average velocity between there and there. And it wasn't going that fast the whole time, right? It's wanting the instantaneous velocity. So what we need to do is find the slope of the little tiny line that exists right here. Okay? But it's so small that we can't see it. We can't get 2 points. We can't do y equals mx plus b because it's too small. All right? So what we have to do is make it longer. So we draw a tangent line. Okay? And a tangent line looks like this. All right? So a tangent touches a curve at a point but doesn't cross it. Okay, so the line that I've drawn here touches the curve at this point, but doesn't cross it, which means at this point, this line is parallel to the curve. If it's parallel, does it have the same slope? Yeah. So can I calculate the slope of that line? Yeah, it's definitely long enough, right? Okay. In fact, I don't even need to use y equals mx plus b here. I can just use v equals d over t and find the velocity here, okay? Because I know that it's at 10 meters here, okay? Although it'd be kind of tough because I don't really know where this line goes here. So what I'm going to do is I'm actually going to go between these 2 points right here, this point and this point. All right, so from time 6 to time 18 seconds, right? So that's going to be 12 seconds. Okay, the object goes from 2 meters to 10 meters. All right, so I've got 8 meters here. I've got 12 seconds there. Can I go v equals d over t? Now I found the instantaneous velocity here. All right, okay. What's the instantaneous velocity at point B? How do you know? Yeah. Okay. If I draw a tangent that touches the curve at point B, its slope is 0. Okay. Because what's going on in part B is the object is slowing down, slowing down, slowing down. The line's getting flatter and flatter and flatter. And then after point B, it's negatively accelerating. Okay, and then here, when we start getting past this point here, okay, the object is now doing what again? Slowing down, right? This line's getting flatter again. Okay? Anytime the line gets flatter, we're slowing down. What's this a graph of? That's a tough one. It's a graph of this. Okay, part A is where I'm throwing the marker. Okay, I'm accelerating the marker. As soon as it leaves my hand, what's grabbing it? What's gravity doing to it? Pulling it down. So it slows down at its maximum height, the highest point. It's actually stopped for an instant, and then it accelerates back down. That's why both sides of this graph are the same, because it's gravity that's doing the work here, okay, on both sides. So gravity affects it equally going up or down. And then after this is where I catch it, bring it to a stop. Okay. That's where we're headed, is being able to look at a graph and figure out what kind of thing is actually going on in this graph. Okay? I can interpret a graph. I can say this is accelerating, this is moving at a constant speed. What does that look like? Okay? That's what we have to get to, is can I look at a graph and know what that motion would look like? Okay. So with velocity versus time graphs, I'm going to give you guys actually a little break here. Give you about 3-4 minutes. Okay. Then we'll talk about velocity versus time graphs. Okay, so on this slide, I've got 2 different graphs, okay? The first graph is a position versus time graph, and this one is a velocity versus time graph, and that line shouldn't be on there. Okay. What's happening on this position versus time graph? What is this object doing? What's that? Okay, going somewhere, how? Accelerating, constant speed? Constant speed, right. This is an object traveling at a constant velocity in a forward direction. Okay, we know that because the line is linear. Okay, it's going the same, it's covering the same displacement each time interval. Everyone okay with that idea? What's that velocity versus time graph showing? The same thing. Okay, remember, this is now a velocity versus time graph. And while it's showing a flat line, that doesn't mean the object's not moving. It means its velocity is not changing. So an object traveling at a constant velocity looks different on a velocity time graph than it does on a position versus time graph. Okay? In fact, these graphs are of exactly the same motion. Right? And I'll prove it to you. Can I calculate the velocity of this object? Okay, so what I'm going to do is I'm going to calculate the slope of the line on that graph. All right, so I'm going to go y minus b over x. Okay, so I'm going to use this point here as my point. So the y value there is going to be 1400. B is 100. And x is 5 seconds. All right, so I got 1300 divided by 5 should be 260. Right? Is that about where the line is on that velocity versus time graph? Right? Here's 200, 250. It's just a little bit above 250. Okay? They're showing exactly the same thing. Okay? Other proof. What's the displacement of this object? $1,300 meters, right? That's final position minus initial position. 1,400 minus 100. Okay, everybody with me there? All right. On this graph, the graph is telling me I'm traveling at a speed of 260 meters per second for 5 seconds. Can I calculate the displacement? Is it going to be 1,300? Yeah, because this is 260 in 5 seconds, right? 265 seconds, right? So D equals V times T, 260 times 5 is 1,300 meters. Okay, these graphs are showing exactly the same motion. Right? Okay, on this velocity versus time graph, what would an accelerating object look like? And I mean, by accelerating, I mean an object that's going faster. Ethan? Right, a line with positive slope. So this. Okay, that would be an accelerating object. Okay, showing that the velocity is changing and getting faster. What does that line look like on this graph? A curve. Okay, it would look like that. That's what we've got to be able to do. Okay, it'd be very easy for a question to say, here's two graphs, are they showing the same thing? Okay, or here's a velocity versus time graph. Draw a rough sketch of what the position time graph of this motion would look like. Okay, it'd be very easy for them to do that, to see whether you can go back and forth on interpretation of what these graphs should look like. Okay, now something we haven't talked about in terms of things that you can get from a position versus time graph. Okay, we have talked about that. We can calculate displacement from a position versus time graph. We can calculate velocity from a position versus time graph. We can calculate distance and speed from a position versus time graph. Okay, a velocity versus time graph, we can calculate some other things. Okay, I can calculate displacement. I just did it. Okay, calculate displacement from a velocity versus time graph. But I can't calculate speed. I can read speed and velocity directly off this graph, okay, because that's what it's showing. So I don't need to calculate speed or velocity. I can read them off of this graph. But there's something on this graph that I can calculate that I can't calculate with a position time graph. Acceleration. Okay? I can actually calculate how fast is the object going faster. That's what acceleration is, okay? Your rate of change of velocity. So if I have a velocity versus time graph that looks like this, okay? It's showing meters per second here and seconds here. So we just said that this line then means that the object is accelerating, that it's picking up speed or going faster, okay? Acceleration is your rate of change of velocity. If you look on your formula sheet, you'll see this formula. That acceleration equals final velocity minus initial velocity divided by time. Okay? Does that look, again, a lot like this formula? Okay? Same format, right? Something minus something over something else, right? Well, since this is a velocity versus time graph, B would be our initial velocity. Over here would be our final velocity, and then x is once again our time, okay, because time is on the x-axis. So we can calculate the acceleration of an object from the slope of this graph. All right, we're going to do an activity next week where we'll look at that a little bit more, okay? But that's the kind of stuff we can get off of a velocity versus time graph. And we can also calculate displacement from the velocity versus time graph. So we did that with this line here, with the level line. Could I calculate it here? Could I calculate the displacement for this line? Okay, I can. How would I do it? Okay. Yes. Okay. So you're on, yes, on the right track here. All right. So if I want to calculate the displacement, when I calculated the displacement of this level line, I just did this. D equals V times T. So essentially what I did is I took the base of the rectangle and multiplied it by the height of the rectangle, right? The height of the rectangle was 260 and the length of the rectangle was 5 seconds, right? Well, the same is true for this line. Okay, all I did was take average velocity and multiply it by time. I can do the same thing for this line. Even though the speed is changing, there's still an average there. Agreed? Where's the average occur? In the middle. Okay, how do you calculate the area of a triangle? Base times height divided by 2. Well, the height is showing my velocity. Half of the height, or the height over 2, would be my average velocity. And if I multiply that by the base, I'm multiplying by time. It's exactly the same calculation that I did up here. Okay, so I can calculate the displacement of an object on a velocity time graph by calculating the area under the line, because that's average velocity times time. Okay, this is a graph of a runner in a sprinting race. What are they doing at the beginning? They're accelerating, yeah. Okay, you come out of the starting blocks and you're going faster and faster and faster and faster. Now, no matter who you are, you run as hard as you can. Eventually, you can't run any faster, okay? It's just, you know, things balance out. You can only exert so much force. It's balanced by wind resistance and whatever else, okay? You can't run any faster. That would be this part of the graph, okay? And then, what do? Not just slow down, they actually, well, no, they don't go backwards. This is a velocity time graph. The velocity is never negative. Stop, right? Doesn't their velocity become 0? Okay, so this is slowing down to a stop. Okay, now if they were going backwards, I would have to extend the graph down into the negatives, and then this line would go like that. So it would be like I'm running, and then I hit a bungee cord. Okay, so I slow down, and then start moving backwards. Okay, and then yeah, my graph would go into the negatives, okay? Because I would actually be moving with a negative velocity then going backwards. Okay, I kind of already diagrammed that, but I didn't talk about units. Okay, so for acceleration, okay, we said acceleration can be calculated from a velocity versus time graph using slope or using this formula. Probably write that down somewhere. Okay, this is our formula for acceleration, VF minus VI over T. I'm just going to make that a little bit neater. Oh. Okay, so we got to look at what are the units for acceleration here. What do we get? Okay, when we calculated the slope of the line on the position versus time graph, we were dividing meters by seconds, and we got meters per second, which were the units for velocity. Okay, when we calculate the slope of the line on the velocity versus time graph, okay, I'm taking meters per second and I'm dividing that by seconds. Okay, I'm taking velocity and dividing by time, right? The seconds don't cancel here, okay? This is like dividing fractions. So I've got meters per second divided by seconds. Seconds over 1, really, right? So when you're dividing fractions, what are you supposed to do? Multiply by the reciprocal, okay? So that means instead of this, I have that. What's meters times 1? Meters, right? Okay, so I've got meters. What's seconds times seconds? Seconds squared. Okay, our units for acceleration are often written as meters per second squared, but what they really are meters per second. Okay, how fast are you changing your velocity? I'm changing my velocity by this many meters per second every second. Meters per second, or meters per second squared. Okay, everyone follow me on that? Okay, to give you some idea, okay, if you were to like fall, you would accelerate at this rate. This is the acceleration due to gravity average on Earth. Okay, so if you're falling on Earth, every second you fall, you will accelerate by 9.81 meters per second. Okay, that means that if you fall for 2 seconds, you are now falling faster than you can run. Okay, that's pretty extreme acceleration. Yes, in the real world, after a few seconds, you reach what we call terminal velocity, okay, which means you can't accelerate anymore. And that's due to air resistance. Okay, the force of gravity becomes balanced by the force of you going through the air, and as a result, you can't go any faster. Now you can change that depending on your shape. If you've ever watched professional skydivers, that's what they do. Okay, if they want to fall really fast, okay, they tuck in like this, and they put their head back, and they put their arms and legs kind of in a line, and they can fall really quickly. If they want to fall slowly, they go spread eagle, okay, and they increase their air resistance, and they fall more slowly. Right? So terminal velocity can be affected by how aerodynamic you are. Right? But we don't ever deal with that. We deal with the perfect physical world where you will accelerate all the way to the ground, okay? Which means you'll be going really fast by the time you hit the ground. Okay, and that's not actually the way it really works. Okay. All right, so this is just kind of what we've talked about, but written out in words for you, so you have this in your notes. On a velocity versus time graph, the vertical value of any point is the velocity, instantaneous velocity at that point, okay? And the area under the line on a velocity versus time graph is the displacement of the object. And the thing I forgot to write on here is that the slope of the line represents acceleration. Okay, those are the things that we can calculate and read from a velocity versus time graph. All right, so we're going to spend most of next week working on graphing. Graphing is an absolutely fundamental skill for all of the sciences, but physics and chemistry especially. Okay, I want you guys to try to do this question here. So I've got a position versus time graph. I want you to calculate the total displacement, the total distance, the average velocity, and the average speed of the object. Okay, the answers are there in bold. You can see if you did it right or not. Okay, give you a couple minutes on that, and we'll go through it before the bell goes, hopefully. Okay, have a good weekend. We'll talk about that one on Monday. Oh, still recording. Thanks.